Boom. There we go. Hello and welcome back to Calculus 1. The next section is on infinite limits. Now, what this means is your answer is one type of infinity. So you will approach the limit to a value a, and you will get negative infinity or positive infinity. So this is what we are looking for. So it's called infinite limits because the answer is one of the infinities. So let's see the example of this. Say you have a good old limit x approaches 0 of 1 over x squared. We know from before that that's positive infinity. Right, we did that earlier because the graph looks like this, and you see the approach from the left is positive infinity. The approach from the right, it's positive infinity. Overall, positive infinity. And the lecture is over. But then we can dig a little bit deeper and find extremely important definition and the use of these infinite limits. And that will be the definition for the vertical asymptote. So now you're finally going to learn what the vertical asymptote actually is. I know you used it before. So vertical asymptote. What is happening here? If f of x has limit x approaching a minus as positive or negative infinity, or limit x goes to a plus of f of x is equal to positive negative infinity, then there is a vertical asymptote at x equals a. So this definition helps you figure out that there is a vertical asymptote for a function. So does this definition work for, let's say, 1 over x? Does it? Does it work? Do we have vertical asymptote for 1 over x? Come on, yes or no? Yes. Limit x approaches 0 minus for 1 over x is negative infinity. There you go. This implies VA at x equals 0. Immediately. You don't have to compute anything else. 1 is enough. Only one-sided limit needs to go to infinity. There's a vertical asymptote there.
So I get that you get against 0, right? That's
yes, because that was my suspicion.
to 1 divide. You don't basically 1 divide.
No, I look at a graph. I know how the graph looks like. Because I skipped over it because we did it.
Yeah, it's the same graph.
Approach from the left. I want to do it red. Approach from the left shoots down to negative infinity. Right? So that's why there is a vertical asymptote at x equals 0. Oh, by the way, one thing that I'm extremely allergic to is you writing this. That has no meaning. This carries no points on the test. No partial credit. No, nothing. Because this is just nothing. the equations of the line are x equals a number for vertical lines and y equals a number for horizontal lines. So make sure you have that, otherwise you trip my allergies and then I'm not okay after that. Let's see the next example. Limit x minus 5 over x squared minus 25 as x goes to 5. How many vertical asymptotes here? One. At 5? Forget about the limit here for now. How many vertical asymptotes do we have? I'm going to recast these problems. Here. So f of x is equal to x minus 5. So what do we get? 1 or 2 verticals or none? What do you think? You say 1. That's correct. It's 1. But you'll learn that if you set denominator equal to 0, that's where the vertical asymptotes are, right? And that will give you positive and negative 5. Why?
Because 5 minus 5 is 0, and 5 squared is 25 minus 25 is 0, 0 is 0. This is not. Right?
So why is it just 1?
All right. So this is types of problems that you're not going to see in your pre-calculus because you don't have the limit definition to prove asymptotes. So this is a very quick problem, guys. X minus 5 divided by x minus 5, x plus 5. Boom. And we get 1 over x plus 5. What's the only number that will make the denominator 0? Negative 5. So, to prove that the only asymptote is at negative 5, say, well, how about 5? Because in original problem, 5 also made 0. So let's try it. You are checking if x goes to 5, whether it's minus or plus, either one, for x minus 5 over x squared minus 25. Remember that definition for vertical asymptote states that if the one of the one-sided limits goes to infinity, it is a vertical asymptote. So now let's try that number 5 and see if it gives us the asymptote. Limit x goes to 5 from the left, x minus 5, x minus 5, x plus 5. These guys cancel. And what do you get? You get 1 over 25. So what is that? Yeah, it's clearly not infinity, so it's not a vertical asymptote. So what do we have at positive 5? What do we have? It's not the point. So we call that open circle, right? So how does the graph look like? We have, it's a hole. So we have a vertical asymptote at negative 5. The problem will do this. And then at 5, we are going to have open circle. Now, if you graph this in your calculator, TI-83, and you zoom in, you are going to see a missing pixel. It's not going to look, if you just have a standard screen, 10 by 10 by 10, right? You're not going to see it. It will look continuous. But if you zoom from 4 to 6, let's say, and from 0 to 1 on Y, the line is going to go through and it will have a missing pixel because you zoomed in enough to see a missing pixel there. So this entire section and the next one to 5 are very short because you are defining the asymptotes and you are learning that these definitions for asymptotes are the way to compute and prove that there is or not, there's not an asymptote there. You just compute the limit. You know how to compute limits. That's your previous sections. We're not learning how to compute limits now. This is application section. So we are now using the limit to show that if the limit is infinity, yes, there is a vertical asymptote there. If the limit is not infinity, it's the open circle. It's one or the other. You have to have one or the other. Ta-da! I hope you're not disappointed. All right, so I will see you all tomorrow. We will cover next two sections. If you missed any of the class preps, bring them.